Communication over a Gilbert-Elliott channel with an energy harvesting transmitter, submitted to ICC 2017. The outline of the presentation is as follows. Due to the tremendous increase in the number of battery-powered wireless communication devices over the past decade, harvesting of energy from natural resources has become an important research area as a means of prolonging lifetime of such devices. The main challenge is that the energy arrives at random times and in random and minuscule amounts. There is a vast amount of research on how to best manage networks with this random energy source. The main body of research lies in the areas of scheduling and routing strategies and also channel access strategies. Sensing the channel always comes at a cost. However, it also increases adaptability to the channel conditions. Channel sensing capability improves the performance significantly. In this work, we incorporate channel sensing into the action set of an EH transmitter. We formulate the problem as a partially observable Markov decision process. Then, by introducing a belief parameter for the channel state, we convert the problem to a Markov decision process with continuous state space. Then, we prove that the optimal policy, maximizing a discounted reward, is a threshold policy on the belief state. Moreover, we prove that the thresholds depend on the battery level of the transmitter. Consider the communication system illustrated in the figure, in which an EH transmitter communicates over a slotted Gilbert-Elliott channel. Let GT denote the state of the channel at time slot t, which is modeled as a one-dimensional Markov chain with two states, a good state denoted by 1 and a bad state denoted by 0. The transition probabilities are given by lambda 1 and lambda 0 as shown in the figure. The transmitter can transmit R bits per time slot if the channel is in good state and 0 bits otherwise. A unit of energy arrives at the end of time slot t according to an independent and identically distributed Bernoulli process denoted by E subscript t with probability q. The transmitter stores the energy packets in a battery with a storage capacity of finite size. An energy unit is consumed at each slot if the transmitter decides to transmit in that time slot. A unit of energy consumed per time slot includes the energy cost of sensing, transmission of the message, and the reception of ACK or NACK from the receiver. We assume that the transmitter has an infinitely backlogged data queue, and thus it always has a packet to transmit. At the beginning of each time slot, the transmitter may choose among three possible actions: deferring the transmission, channel sensing and transmitting opportunistically, and transmitting without sensing. Deferring the transmission, denoted by D, corresponds to the case in which the transmitter either believes that the channel is in a bad state or observes that its battery has low energy. If this action is chosen, there is no message exchange between the transmitter and the receiver. Hence, the receiver does not send any feedback, and therefore the transmitter cannot obtain any knowledge about the current channel state. Channel sensing and transmitting opportunistically, denoted by O, corresponds to the case in which the transmitter decides to sense the channel at the beginning of the time slot. We assume that sensing consumes a fraction tau of an energy unit. We assume that the time it takes to sense the channel is tau seconds, and the transmitter consumes on average the same power as the data transmission over the sensing period. In the remaining 1 minus tau seconds, the transmitter may choose to transmit data at the same rate it would without channel sensing, which means that by the end of the time slot, it transmits 1 minus tau times R bits per time slot. If the channel is revealed to be in the bad state, the transmitter defers its transmission and saves the rest of the energy unit. Note that, thanks to the channel sensing capability, in the case of a bad state, the transmitter wastes only tau portion of a unit and saves the remaining energy by deferring its transmission. Let S be the state of the system. B subscript t is the battery level at time t, and X subscript t is the belief of the transmitter at time slot t. Belief of the transmitter is the conditional probability that the channel is in the good state at the beginning of the current time slot given the past history. For an initial belief P, the expected discounted reward has the following expression as in equation 1. Capital R is the expected reward acquired when action A is taken at state S. Since at least one energy unit is required for transmission, if the battery state is less than 1 unit, the reward becomes 0. Hence, in explaining the expected reward function in equation 2, we consider actions when the battery state is greater than or equal to 1. If the action of transmitting without sensing is chosen, R bits per time slot are transmitted successfully if the channel is in a good state, and 0 bits if the channel is in a bad state. Since the belief represents the probability of the channel being in a good state, the expected reward is given by X times R. If the action of transmitting opportunistically is chosen, tau fraction of energy unit is spent sensing the channel, with the remaining energy being used for transmission if the channel is sensed to be in a good state. In this case, 1 minus tau times R bits per time slot are transmitted successfully. If the channel is sensed to be in a bad state, the transmitter remains silent in the rest of the time slot. The expected reward in this case is 1 minus tau times X times R. Finally, if the action of deferring the transmission is taken, the transmitter neither senses the channel nor transmits, so the reward is 0. Our objective is to find the policy that maximizes the value function at any given state. The value function satisfies the following Bellman equation, which states that at any given state, optimal policy should choose the action that maximizes the action value function. Action value function, denoted by V subscript capital A, is the action value function defined as the expected infinite horizon discounted reward acquired by taking action A when the state is B and P. Next, we will prove that the optimal policy has a threshold type structure on the belief state. First, we need to prove some of the properties of the value function. We begin with establishing the convexity of the optimal value function with respect to the belief state in the first lemma. In the second lemma, we show that the value function is a non-decreasing function of the battery state B. This lemma provides the intuition why deferring or sensing actions are advantageous in some states. The incentive of taking these actions is that the value function transitions into higher values without consuming any energy. Moreover, it states that the value function is also non-decreasing with respect to the belief state P. Finally, the following theorem shows that the optimal solution of the problem is a threshold policy with 2 or 3 thresholds depending on the system parameters. The threshold values also depend on the state of the battery. In the figures, the areas highlighted with blue color correspond to those states at which deferring the transmission is optimal. Green areas corresponding to the states at which transmitting opportunistically is optimal, and finally yellow areas corresponds to the states for which transmitting without sensing is optimal. We investigate the effect of the sensing cost on the optimal policy. We obtain optimal action region for 2 different sensing costs, one being tau equals to 0.2 and the other being tau equals to 0.5. It is evident that a higher cost of sensing results in less incentive for sensing the channel. For this reason, the green areas has shrunk almost to nothing in optimal action region corresponding to tau equals 0.5. Next, we compare the performance of the optimal policy with 2 alternative policies, namely a greedy policy and a single threshold policy. In a greedy policy, the transmitter transmits whenever it has energy in its battery. In the single threshold policy, there are only 2 actions, defer or transmit. We optimize the threshold corresponding to each battery state for the single threshold policy using the value iteration algorithm. Throughput achieved by these 3 policies are plotted in the figure with respect to the EH rate Q. As expected, we observe that the greedy policy performs the worst as it does not exploit the transmitter's knowledge about the state of the channel. We can see that by simply exploiting the ACK-NACK feedback from the receiver, it is possible to achieve a higher throughput than the greedy policy for all values of the EH rate. On the other hand, by further introducing the channel sensing action, the throughput of the system is substantially increased. The improvement is particularly higher for the mid-range of Q values, for which the transmitter benefits more from the flexibility offered by 3 actions. In this work, we have shown that the channel sensing capability improves the performance of the EH transmitter significantly. First, we formulated the problem as a partially observable Markov decision process. Afterwards, by introducing a belief parameter for the channel state, we converted the problem into an ordinary Markov decision process with continuous state space. We proved that the optimal policy is a battery-dependent threshold policy on the belief state. We calculated the optimal threshold values numerically using the well-known value iteration algorithm. Finally, we have shown through simulations that the channel sensing capability improves the performance significantly.